Hidden patterns of balance govern everything in the cosmos. These strange symmetries are the secret rules of reality, from the spin of an electron to the shape of a galaxy. They are the fundamental code we are just learning to read. By the end of this journey, you will understand how these symmetrical principles built the universe and why their breakdown is the very reason you exist. We will uncover why matter survived the Big Bang and investigate the mysterious one-handedness of life itself. What hidden order do you suspect lies beneath the surface of our chaotic world? A snowflake forms in the turbulent chaos of a winter cloud, and yet it descends with a perfect six-sided geometry. This is nature's quiet proclamation that order can and will emerge from randomness. This principle of balance and pattern is not just a beautiful accident. It is the deepest rule in the book of physics. The celebrated physicist Philip Anderson observed that it is only slightly overstating the case to say that physics is the study of symmetry. Think of a simple circle. It looks the same no matter how you rotate it. This rotational symmetry is not just a pleasing shape. It is directly linked to one of the universe's most fundamental laws, the conservation of angular momentum. The reason an ice skater spins faster as she pulls her arms in is written in that symmetrical code. This connection is universal. The fact that the laws of physics are the same today as they were yesterday, a symmetry in time, gives us the conservation of energy. The fact that an experiment works the same in your lab as it does in mine, a symmetry of location in space, gives us the conservation of momentum. These are not just abstract ideas. They are the invisible scaffolding that holds reality together, from the way particles interact in the void to the incredible stability of the atoms that make you and everything you see. But this perfection presents a profound puzzle. If symmetry is so absolute, so deeply embedded in the cosmos, then why does our universe look the way it does? Why is it filled with things, with planets and stars and life, instead of just a featureless, symmetrical sea of energy? The answer lies in the most creative force in the cosmos. What happens when a perfect symmetry breaks? That perfect cosmic symmetry had to break for our universe to be born. The most dramatic evidence for this lies in a single, staggering fact. For every 1 billion particles of matter created in the Big Bang, there should have been 1 billion particles of antimatter, identical in mass but opposite in charge. These mirror versions of particles are destined to annihilate each other on contact, vanishing into a flash of pure energy. In a perfectly symmetrical universe, this is exactly what would have happened. All matter and all antimatter would have completely destroyed one another, leaving behind a cold, empty, and eternal sea of light. There would be no atoms, no stars, no planets, and certainly no one to ponder this mystery. The fact that you are here to hear this means something went wrong with that perfect symmetry. Something tipped the scales. Physicists call this the problem of baryogenesis, the mystery of how a universe of stuff came to be. The culprit appears to be the violation of a deeply held principle known as CP symmetry. CP stands for charge and parity. It is an elegant idea stating that the laws of physics should be identical if you simultaneously swap a particle with its antiparticle, which is the charge conjugation, and view its reaction in a mirror, which is the parity transformation. In a CP symmetric world, a reaction involving matter should look exactly the same as its mirror image reaction involving antimatter. It is the ultimate expression of cosmic fairness. But our universe is not fair. In the 1960s, scientists studying the decay of strange particles called neutral kaons found something shocking. The decays of these particles and their antiparticles were not perfect mirror images. There was a slight but definite difference. It was as if a left-handed clock and a right-handed clock ticked at subtly different rates. This was CP violation in action. Decades later, much larger experiments at particle accelerators like CERN, using particles called B mesons, confirmed this lopsidedness with even greater precision. The imbalance is tiny, a fraction of a percent, but in the furnace of the early universe, that tiny preference was everything. For every 1 billion annihilations, one single particle of matter was left over. That 1 in a billion remnant is the entire material universe. Every galaxy, every star, every planet, and every one of us is made from that fragile surplus, the leftover ash from a near-total annihilation. This fundamental lopsidedness is not a minor detail. It is the reason anything exists at all. That same cosmic lopsidedness, the one that left us a universe of matter, might be written into the very fabric of life. Look at a simple screw. Its spiral thread is designed to turn clockwise to tighten, a specific handedness we take for granted. Now, consider the molecules that build your body. They have a handedness too, a property scientists call chirality. Just as your left and right hands are mirror images that cannot be perfectly superimposed, many molecules come in left and right-handed versions. And here is the profound mystery. All life on Earth makes a unanimous and exclusive choice. The proteins that form your muscles, your hair, and your enzymes are built exclusively from left-handed amino acids. The sugars that form the backbone of your DNA are exclusively right-handed. This universal preference is known as biological homochirality, and it is a broken symmetry as fundamental as the matter-antimatter imbalance. Why would life choose one hand over the other? It is a puzzle that reaches back to the dawn of our solar system. Analyses of meteorites that have fallen to Earth reveal an excess of left-handed amino acids, suggesting this bias might have been delivered from space, predating life itself. The leading theory points a finger directly at the fundamental forces. The weak nuclear force which governs radioactive decay is the only force that violates mirror symmetry. It is inherently left-handed. This means that particles like electrons emitted during certain decays are always spinning in a left-handed way. In the primordial soup of the early solar system, bathed in the faint, polarized light from newborn stars that were themselves shaped by asymmetric forces, this inherent bias of the weak force could have ever so slightly degraded one form of a molecule over its mirror image. Over millions of years, this tiny preference, amplified by crystallization and other processes, could have tipped the scales, creating a reservoir of left-handed amino acids in the dust and ice that would later form planets. The homochirality of life, then, is not a random accident of biology. It could be a fossilized echo of the universe's deepest asymmetries. The same fundamental lopsidedness that spared a handful of matter from total annihilation may have also guided the assembly of the very first building blocks of life, connecting the fate of exploding stars to the spiral of your DNA. This cosmic preference for one hand over the other finds a powerful echo in the very origin of mass. Think of a ball perfectly balanced on the crest of a rounded hill. The situation is perfectly symmetrical. The ball could roll down in any direction with equal ease, but that perfect balance is unstable. The slightest breath of wind, the smallest vibration, will send the ball tumbling into one specific valley below. The symmetry of the hilltop is broken, and the ball finds itself in a particular stable state. This simple analogy captures the essence of one of the most profound discoveries in modern physics, the Higgs mechanism. In the earliest moments of the universe, a field known as the Higgs field is thought to have permeated all of space, possessing a similar high degree of symmetry. In that intense heat, elementary particles like electrons and quarks raced around at the speed of light, utterly massless. But as the cosmos expanded and cooled, a cosmic transition occurred. The Higgs field, like that ball on the hill, could no longer maintain its symmetrical but unstable state. It settled into a specific, stable value everywhere in the universe. This event was a symmetry breaking on a cosmic scale. As it settled, the Higgs field began to interact with particles, not as a force, but as a kind of cosmic drag. Some particles, like photons, pass through it completely unaffected, remaining massless. Others, like electrons and quarks, interact with it strongly, slowing down and acquiring the property we experience as mass. Without this pivotal break from perfect symmetry, the fundamental building blocks of atoms would have no mass. They would forever fly at light speed, unable to bind together. There would be no atoms, no chemistry, no solid matter. The universe would be a featureless, luminous fog. The tangible structure of our world, from the ground beneath your feet to the stars in the sky, is a direct consequence of that one specific tumble from a symmetrical peak into a particular valley, a moment when the universe chose to become solid. This theoretical shadow universe, where every particle has a hidden twin, is more than just a physicist's fantasy. It is a grand idea known as supersymmetry. The cosmos is built from two distinct families of particles. There are fermions like electrons and quarks, the solid building blocks of all matter, and there are bosons like photons and gluons, the messengers that carry the fundamental forces. Supersymmetry proposes that these two families are not separate at all. It suggests a deep, hidden symmetry where every fermion has a bosonic superpartner and every boson has a fermionic twin. The electron would be paired with a theoretical selectron, the photon with a photino. This would double the number of elementary particles, creating a much more symmetric and elegant picture of reality. Why propose such a thing? This idea solves some of the most nagging problems in physics. One is the hierarchy problem, a question of why gravity is so unimaginably weaker than the other forces. The math suggests the Higgs boson, the particle that gives others mass, should be incredibly heavy, yet it is surprisingly light. Supersymmetry elegantly fixes this. The contributions from regular particles and their superpartners would cancel each other out, naturally explaining the Higgs's lightness. Even more compelling, the lightest of these superpartners would be stable, invisible, and pervasive throughout the cosmos. It would not interact with light, yet would have gravity. It fits the description of dark matter perfectly, but for all its mathematical beauty, nature has so far kept its superpartners hidden. The most powerful particle colliders, like the Large Hadron Collider, have searched for any sign of these shadow particles and found nothing. This lack of evidence is a profound puzzle. Yet the theory's power is so great that many physicists feel it must be true in some form. It is a cornerstone of string theory, the ambitious attempt to unite all forces and particles into a single framework. Supersymmetry represents a hope, a belief that beneath the broken symmetries we see lies a deeper, more perfect order waiting to be discovered. The ultimate map of creation is painted in the faintest light. This is the cosmic microwave background, the cooled and redshifted afterglow of the Big Bang itself. For decades, it appeared to our instruments as a nearly perfect, uniform glow, a cosmic sea of microwaves bathing the entire universe. But this perfection was a mask. When we finally learned to read this ancient map with exquisite precision, we discovered it was not a featureless blank. Etched across its entire surface are tiny variations in temperature, fluctuations of just a millionth of a degree. These are not the chaotic scars of a violent birth. They are something far more profound. These fluctuations exhibit a specific kind of order, a statistical symmetry known as Gaussianity and isotropy. This means the variations are distributed in a smooth, balanced pattern across the entire sky, with no preferred direction or special location. The hot and cold spots are like the crests and troughs of a perfectly calm sea, a signature of pure randomness, and this specific pattern is the universe's most important fossil. It tells us that these colossal ripples began as unimaginably tiny quantum fluctuations, random jitters in the fabric of space-time itself when the cosmos was smaller than a single atom. In the first fraction of a second, a theoretical period of hyper-expansion called inflation stretched these quantum seeds from the microscopic to the cosmic. What was once a subatomic tremor became a continent-spanning ripple in the energy of the young universe. As the cosmos cooled and this energy condensed into matter, these imprinted ripples became the gravitational blueprint for everything to come. Slightly denser regions, seen as slightly cooler spots on the map, had a bit more gravity. Over billions of years, they pulled in more and more matter, eventually collapsing into the vast cosmic web of galaxies, clusters, and superclusters we see today. The entire grand structure of the cosmos, every filament of the cosmic web, was seeded by those first symmetrical whispers. The map's incredible uniformity also confirms the shocking flatness of the universe on the largest scales, a geometric symmetry that dictates its ultimate fate. So when you look up at a dark night sky, you are not just seeing empty space between the stars, you are seeing the amplified echo of a quantum hum, a symmetrical pattern written in the first moment of time and stretched across the heavens. This grand design, imprinted at the beginning of time, did not remain a faint temperature map. It grew into the largest structure we can possibly observe, a cosmic web of staggering scale and beauty. If you could pull the camera back far enough to see billions of light years in a single glance, you would not see a random scattering of galaxies. You would see a vast, interconnected network, a sprawling architecture of brilliant filaments and great walls where galaxies cluster like beads on a string. These luminous threads surround and define immense, dark, and nearly empty voids, regions of space that can be hundreds of millions of light years across. This is not chaos, it is a specific kind of order, a statistical symmetry known as scale invariance. It means the universe looks roughly the same, no matter what scale you observe it. The way galaxies cluster together in a local group mirrors the way those groups cluster into superclusters, and those superclusters form the even larger filaments. It is a fractal-like pattern of structure within structure, all tracing back to those initial, symmetrical seeds in the cosmic microwave background. This entire cosmic metropolis was built by one relentless, asymmetric force, gravity. While the initial seeds were perfectly balanced, gravity is the great amplifier of imbalance. It is a force that only pulls, never pushes. A region of space that was ever so slightly denser than its surroundings had a tiny bit more gravity. Over billions of years, that small advantage allowed it to pull in more and more matter from its neighborhood, growing denser and stronger, while the less dense regions were emptied out, becoming the great cosmic voids. The filaments and walls we see are the watersheds of the cosmos, the channels where matter finally pooled after flowing for eons under gravity's one-way pull. So these colossal filaments are more than just the largest things in the universe. They are a frozen record of cosmic history, a direct consequence of symmetric beginnings molded by an asymmetric force. They are the final, magnificent expression of a pattern whispered at the dawn of time, now written across the sky in galaxies and light, spinning within the brilliant disk of our Milky Way. The stars themselves are merely the visible decoration on a structure of far greater scale and mass. This luminous spiral is embedded within a vast, invisible sphere, a halo of dark matter that extends far beyond the last visible star. We cannot see it, we cannot touch it, but its gravitational embrace is what holds the entire galaxy together, preventing it from flying apart as it whirls through the void. The profound mystery is not just that this dark matter exists, but the specific, elegant shape it takes. Through sophisticated computer simulations of cosmic evolution, a clear picture has emerged. These dark matter halos are not chaotic or irregular. They possess a deep and surprising symmetry, a universal density profile that appears to hold true from the smallest dwarf galaxies to the largest galaxy clusters. The most famous of these, known as the Navarro-Frenk white profile, describes a halo that grows dramatically denser towards its center in a smooth, mathematical curve. This is a cuspy halo with a steeply rising core of invisible mass. How does something that does not interact with light and barely seems to interact with itself arrange itself into such a clean, predictable, and symmetrical form? The answer is written in the one language dark matter understands perfectly, the language of gravity. Billions of particles, influenced only by this single, relentless force, naturally settle into this state of balanced equilibrium over cosmic time. It is the most fundamental shape that pure gravity carves out of the dark. This universal symmetry is not just a curiosity. It is one of our most powerful clues in the hunt to identify what dark matter actually is. The precise details of the halo's profile, the steepness of its central cusp, and its overall structure act as a strict test for any proposed candidate. Could dark matter be a WIMP, a weakly interacting massive particle that rarely bumps into anything? Or is it an action, an incredibly light wave-like particle born from theories attempting to solve other cosmic puzzles? Each possibility would leave a subtly different fingerprint on the shape of these halos. The clean, symmetrical shadow that cradles our galaxy is therefore a cosmic signature, a gravitational autograph waiting to be decoded. It holds the secret to the invisible architecture of the universe, the hidden framework upon which all the light and beauty of the cosmos is hung. Deep within the gravitational heart of a galaxy, a black hole presents us with a symmetry of absolute simplicity. According to a fundamental theorem, a stationary black hole is defined by just three numbers: its mass, its electric charge, and its spin. This is the famous no-hair theorem. It means that every single detail about the matter that collapsed to form the black hole, every atom, every chemical composition, every memory of what it once was, is utterly erased from the universe. Whether it was a collapsing star made of iron or a cloud of pure hydrogen, the resulting black hole from the outside would be perfectly identical. This is a symmetry of forgetting, a final, stark equilibrium. But this perfect simplicity creates one of the greatest conflicts in all of physics, the black hole information paradox. Quantum mechanics, the rules governing the very small, insists that information can never be truly destroyed. It can be scrambled but never lost. General relativity, which describes gravity and the large-scale structure of space-time, seems to demand that information vanishes forever behind the event horizon. So which is it? Is the black hole the ultimate shredder, permanently deleting the cosmic hard drive? Or is the information somehow preserved, hidden in a way we cannot yet see? This paradox suggests that the perfect, silent symmetry we see from the outside might be an illusion. The event horizon could be a turbulent surface of quantum activity, a scrambled hologram encoding all the information of what fell in. The quest to resolve this forces us to confront the deepest questions about reality. What is the true nature of information? Is it a physical thing, woven into the fabric of space-time itself? The bizarre symmetry of a black hole, an object defined by so little, may ultimately hold the key to unifying our understanding of the entire cosmos. This dance between information and reality reaches its most radical expression at the edge of a black hole. The information that falls in seems to be lost forever, yet the event horizon's area, a two-dimensional surface, seems to hold a record of it. This paradox gave birth to a staggering idea, the holographic principle. What if everything contained within a volume of space, every star, every planet, every person, is actually encoded on its boundary, like a three-dimensional image projected from a two-dimensional surface? This is not science fiction. It is a serious proposal that redefines the nature of reality itself. A specific and powerful realization of this is known as the AD-SCFT correspondence. It is a precise mathematical duality, a perfect symmetry between two theories that appear utterly different. On one side, you have a theory of gravity operating within a certain warped volume of space. On the other side, a quantum field theory with no gravity at all lives on the lower dimensional boundary of that volume. These two descriptions, one with gravity and three spatial dimensions, and one without gravity and one less dimension, are completely equivalent. They are two different languages telling the exact same story. What does this mean for our universe? It suggests that the space we move through, the three-dimensional world we experience so vividly, might not be fundamental. It could be an emergent property, a holographic illusion generated by a vast, complex network of quantum information living on a distant, two-dimensional surface. The solidity of your hand, the depth of the night sky, all of it could be a projection. This is a symmetry so deep it challenges our most basic assumptions. The universe may not be a collection of things in a void, but a computation, a relationship. The very fabric of space-time could be woven from entangled quantum bits, emerging from a hidden, lower-dimensional reality where the true laws of physics are written. The elegant simplicity of a black hole's three defining numbers stands in stark contrast to the bewildering complexity of the particle zoo. Here, in the realm of the very small, the universe reveals a different kind of pattern. The quarks that build our protons and neutrons are not solitary entities. They come in 6 distinct flavors, whimsically named up, down, charm, strange, top, and bottom. These are not independent actors but are deeply, mysteriously intertwined. They are linked by a mathematical key known as the Kabibbo-Kobayashi-Maskawa matrix. This complex formula describes how quarks of one flavor can transform into another through interactions with the weak nuclear force. This mixing is a sign of a broken symmetry, a subtle imbalance between the three generations of quarks. Why should an up quark be more likely to turn into a down quark than a strange quark? The specific values in this matrix are not derived from any deeper theory. They are fundamental numbers written into the fabric of reality, and we have no idea why they are what they are. This same phenomenon echoes with the ghostly neutrino. Neutrinos come in 3 flavors too, and as they travel through space, they do not stay the same. They oscillate, seamlessly morphing from an electron neutrino to a muon neutrino to a tau neutrino. This dance is choreographed by another matrix, the Pontecorvo-Maki-Nakagawa-Sakata matrix. Like the quark matrix, its angles are arbitrary cosmic constants. Why does the universe contain exactly 3 generations of these fundamental particles? Why not 2 or 4 or 1? The specific mixing patterns are a code we can measure but cannot yet decipher. This broken flavor symmetry is one of the most profound and beautiful puzzles in all of science, a reminder that the deepest laws of nature are written in a language we are only just beginning to learn. That profound scale invariance we see etched across the cosmos has a startling implication. It suggests that in its very first moments, the universe possessed a symmetry even more perfect than we have described. It may have been conformally symmetric. This is a universe without a ruler. In such a state, there is no fundamental unit of length, no absolute sense of big or small. The laws of physics would have been identical whether you were observing a volume of space the size of a single atom or a volume spanning trillions of light years. It is a difficult state to picture, a reality without any inherent scale, where a subatomic fluctuation and a galactic supercluster are, in a deep physical sense, the same thing. This ultimate symmetry is a cornerstone prediction of the theory of cosmic inflation. That brief hyper-expansion did not just make the universe large. It effectively ironed out any pre-existing wrinkles and erased any primordial rulers, leaving behind a perfectly smooth, scale-symmetric vacuum. Then, as inflation ended, that perfect symmetry broke. The energy driving the expansion decayed, reheating the cosmos and filling it with a hot, dense plasma. It was in this transition that the quantum jitters of the inflattened field itself, tiny fluctuations that were once scale-symmetric, were stretched to macroscopic proportions and frozen into the fabric of spacetime. They became the seeds for all future structure, carrying the indelible, scale-invariant pattern that our most powerful telescopes now read in the cosmic microwave background. This is the primary evidence for inflation, the specific statistical signature of those temperature variations. The way the hot and cold spots are distributed is a direct fossil of that brief, perfect epoch. Of course, this perfect symmetry is utterly broken today. We live in a world defined by specific scales. An atom has a definite size, a planet has a fixed diameter. You have a particular height. These are all consequences of the universe acquiring fixed constants, like the strength of gravity and the mass of the electron, which introduce absolute scales into physics. The existence of a ruler of things with definite sizes is proof that the conformal symmetry of the infant universe had to shatter. Yet its ghostly fingerprint remains, written across the entire sky, a permanent record of a time when the cosmos had not yet chosen to be big or small, but was simply and perfectly itself. This abstract dance of phase and particle reveals a symmetry so fundamental it builds reality from the ground up. Think of the quantum wave function of an electron, a mathematical description of its state. Now, imagine you decide to change the phase of this wave, essentially rotating it by a certain angle. On its own, this shift is completely unobservable, a change in description that has no physical consequence. This is a global symmetry, and it is interesting but not particularly powerful. But now, take it a step further. Imagine you have the freedom to change the phase by a different amount at every single point in space. You twist the wave here, you rotate it over there, all independently. In a naive world, this would create a chaotic, inconsistent mess. The description of the electron would be different in New York than it is in Tokyo for no good reason. Yet, for the laws of physics to remain consistent and respect this local phase freedom, something miraculous must happen. The universe is forced to introduce a new field, a gauge field, that connects all these arbitrary local choices, smoothing out the differences. This required field is the electromagnetic field, and its quantum particle is the photon. The very existence of light, of the force that holds atoms together and lets you see these words, is mandated by this profound demand for local symmetry. This is gauge symmetry. It is not a symmetry of objects moving through space, but a symmetry of the laws themselves under a transformation that you are free to make at every location. The perfect one over R-squared law of electromagnetism, the way its strength fades with the square of the distance, is not an arbitrary rule. It is the unique mathematical consequence of this U of one gauge symmetry. This single, elegant principle became the template for all of physics. The strong nuclear force which glues quarks together inside protons, arises from a more complex SU3 gauge symmetry. The weak nuclear force comes from an SU2 symmetry. The entire standard model of particle physics, our most complete catalogue of the universe's building blocks and their interactions, is essentially a tapestry woven from these required local symmetries. The forces we experience are not just features of the world. They are the inevitable physical manifestations of the universe's deepest need for consistency, a demand for harmony written into the quantum code of reality itself. From your backyard, the night sky reveals a profound cosmic truth. On the grandest scales, the universe looks the same in every direction. This property, known as isotropy, is a silent declaration that no single direction is special. Combined with the idea that the universe is roughly the same everywhere, a principle called homogeneity, this forms the bedrock of modern cosmology. It is the reason we can speak of a single cosmic history, a story that unfolds the same way for every distant galaxy. This grand symmetry is not an assumption. It is powerfully confirmed by the cosmic microwave background, that ancient light from the infancy of everything, which bathes us in a uniform glow from all points in the sky. Yet the deepest scientific stories are never quite that simple. As our maps of this ancient light have grown more precise, subtle, puzzling features have emerged. One is nicknamed the axis of evil, an unexpected alignment of hot and cold spots across the cosmos that seems to suggest a preferred direction. Other observations hint at vast rivers of galaxies, colossal bulk flows, moving in a coordinated way across billions of light years, as if pulled by something beyond our observable horizon. These are not errors, they are whispers, tiny cracks in the facade of perfect isotropy. They hint that our universe, for all its apparent uniformity, might have a subtle grain to it, a preferred direction imprinted from its very first moments. This does not break our understanding, but it deepens the mystery. It suggests that the primordial reality was more complex than our simplest models can describe, and that the universe's greatest symmetry might be woven with the faintest threads of direction, a hidden architecture waiting to be read. The fundamental laws of physics are indifferent to the flow of time. If you could film the intricate dance of two electrons colliding and then play the recording in reverse, the reversed events would still perfectly obey every equation we have, from Newton to quantum theory. At this most basic level, the universe does not distinguish between past and future. It is a perfectly symmetrical stage, yet we live in a world where time has a clear and irreversible direction. A shattered glass does not reassemble itself on the floor. The heat from your coffee dissipates into the cool air of the room, never to spontaneously gather back into the cup. We remember yesterday with clarity, but tomorrow remains a mystery. This is the great paradox of the arrow of time, a global asymmetry emerging from perfectly symmetrical laws. The key to this puzzle lies in a concept known as entropy, which is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. It is the only fundamental law in all of physics that gives us a direction, an arrow. But for this arrow to exist, for there to be a drive toward higher entropy, the universe must have started in a very special condition. It had to begin with its entropy incredibly, improbably low. Think of a brand new deck of cards perfectly ordered by suit and rank. This is a state of low entropy. Shuffle that deck just once and you have increased its disorder. You could shuffle it 1,000,000 times and never, by pure chance, return it to its pristine factory order state. The act of shuffling always moves you toward a more probable, more disordered arrangement. Our observable universe was once that perfectly ordered deck. The Big Bang was not a chaotic explosion but an event of breathtakingly low entropy, a state of exquisite and specific order. All the energy of the cosmos was concentrated in a hot, dense, and remarkably uniform state. From that singular point of order, the only possible direction was toward greater disorder. As the universe expanded and cooled, this drive toward higher entropy became the engine of change. It is why stars radiate their heat into the cold void, why mountains erode, and why life itself metabolizes energy, creating local pockets of order at the greater expense of spreading disorder out into the environment. The flow of time you feel, the unidirectionality of your entire existence, is the universe playing out the single, most statistically probable hand from an unimaginably ordered initial deal. The symmetrical laws provide the rules of the game, but that one-time, low-entropy starting condition gives time its irrevocable arrow. This hidden architecture of mass reaches right down into the heart of the atom itself. The protons and neutrons that form your body are not fundamental points. They are frantic, buzzing complexes of quarks held together by the most powerful force in nature, the strong nuclear force. The theory that describes this is quantum chromodynamics, or QCD, a masterpiece of complexity and subtlety. In its purest, most ideal form, this theory possesses a strange and beautiful symmetry. If we could imagine a universe where quarks were utterly massless, the laws of QCD would treat left-handed quarks and right-handed quarks as completely independent, separate entities. A left-handed quark could not simply decide to become right-handed. This perfect independence is known as chiral symmetry, but our world is not that ideal universe. Quarks do have a tiny bit of mass, and more importantly, the vacuum of empty space itself is not a passive stage. It is an active participant. In our reality, the vacuum is like a superconductor for the strong force. It is filled with a kind of invisible condensate, a soup of quark-antiquark pairs that permeates all of existence. This cosmic background field does not respect the perfect independence of left and right. It mixes them up, locking them together. The perfect chiral symmetry is spontaneously broken. It is as if a perfectly balanced seesaw, representing left and right, has been forced to tip and settle into one specific, stable position. And just as a seesaw that has settled can still wobble, this broken symmetry gives rise to a new, incredibly light particle. This is the pion. In the world of particle physics, the pion is almost a ghost. It is far lighter than any other particle made of quarks, and this lightness is the direct signature of its role as a Nambu goldstone boson, the inevitable wobble that appears when a continuous symmetry is spontaneously broken. These pions are not mere curiosities. They are the carrier particles of the residual strong force, the glue that binds protons and neutrons together into atomic nuclei. Without them, nuclei would fly apart in an instant, but the consequences run even deeper. This breaking of chiral symmetry is what gives the proton and neutron over 90% of their mass. The tiny intrinsic masses of the quarks themselves account for almost nothing. The vast bulk of the mass you experience as the solidity of your own body comes from the pure energy of the strong force field, the frantic motion of the quarks confined within the proton, all set into motion by this spontaneous shattering of a perfect symmetry. The stability of every atom, the very possibility of chemistry, and the tangible weight of the world around you are all gifts from this profound cosmic breaking. The universe had to choose a side to break its own perfect-handedness so that stars and planets, and ultimately you, could have something to stand on. This search for the universe's ultimate code leads us to the edge of pure geometry. There exists a mathematical object of such breathtaking symmetry, that it has been called the most beautiful structure in mathematics, the E8 Lie group. Imagine a perfect crystal, but not in 3 dimensions. This object exists in 248 dimensions, a hyperdimensional lattice of unimaginable complexity, yet governed by an internal logic of absolute perfection. Every facet, every rotation, every possible interaction within this abstract space is defined by a flawless and complete symmetry. It is a symphony of geometry. For some physicists, like the unconventional theorist Garrett Lissy, this is not just abstract art. He proposed that this E8 structure could be the master key, a single symmetrical framework that contains within its intricate geometry every single particle and force we know. In this radical vision, an electron, a quark, a photon, even the elusive Higgs boson are not separate entities. They are merely different facets, different resonant notes of this one fundamental geometrical object. The gravitational force and the electromagnetic force become different expressions of the same underlying symmetrical dance. This E8 theory is without question highly speculative and hotly debated. It remains on the fringes of mainstream physics, a beautiful map that may or may not correspond to the actual territory of our universe. Yet, its very existence speaks to a powerful, almost spiritual conviction that drives fundamental research. It embodies the deep-seated belief that the ultimate laws of the cosmos will not be messy, arbitrary, or complicated. They will be ones of supreme mathematical elegance and symmetry. These exceptional theories, built on these rarest of mathematical symmetries, represent a final frontier. They are the place where the abstract world of pure mathematics and the tangible world of physical reality converge, suggesting a staggering possibility. The universe's source code, the fundamental operating system for everything that exists, might not be written in the language of particles or forces, but in the silent, perfect language of geometry itself. That brief, explosive growth spurt of cosmic inflation was governed by its own unique kind of balance, a temporary symmetry that set the stage for everything. The engine behind this expansion is thought to be a field, the inflaton field. For inflation to work as our observations suggest, this field had to possess a special property known as an approximate shift symmetry. Think of a perfectly flat, endless plateau stretching in all directions. If you take a step in any direction, the height of the ground does not change. This is the essence of shift symmetry, a landscape that remains unchanged as you move across it. This symmetry protected the inflaton field's potential energy, preventing it from draining away too quickly. Instead of plummeting down a steep hill, the field could slowly, gently roll down an almost imperceptible slope. This slow roll is what allowed the universe to double in size over and over again, for just a fraction of a second, transforming a subatomic speck into a volume far larger than our entire observable cosmos. It was this temporary dynamic symmetry that created the vast, flat, and uniform universe we see in the cosmic microwave background, but inflation was never meant to last. As the inflaton field eventually reached the bottom of its gentle slope, that protective shift symmetry broke. The field's pent-up energy decayed violently, reheating the cosmos and flooding it with a hot, dense plasma of particles and radiation. In that moment of symmetry breaking, the inflationary epoch ended and the conventional hot Big Bang began. Cosmic inflation, therefore, is the ultimate symmetry breaker. Its temporary, balanced reign created the perfectly smooth, featureless canvas. Its end, the breaking of that balance, provided the explosive burst of heat and energy that set all of cosmic history in motion, painting the first particles onto that pristine surface. This unbreakable rule of charge, parity, and time reversal stands as a sacred pillar of modern physics. The CPT theorem declares that if you could simultaneously swap every particle for its antiparticle, reflect the entire universe in a mirror, and reverse the flow of time, the resulting world would be utterly indistinguishable from the one we live in now. This three-part symmetry is considered exact and absolute. It is the ultimate cosmic rewind button, and physics demands that the movie plays exactly the same forwards and backwards under this complete transformation. The bedrock upon which this entire principle stands is Lorentz Invariance, the profound symmetry from Einstein's special relativity. This is the simple, revolutionary idea that the laws of physics are precisely the same for every observer moving at a constant speed. Whether you are sitting perfectly still or racing past in a spaceship at 99% of the speed of light, every experiment you perform will yield the exact same results. The speed of light remains constant, and the fundamental rules of reality do not change. This symmetry of motion is what weaves space and time together into the single fabric of spacetime. It is why time slows down and lengths contract for objects moving at incredible speeds, effects that are not illusions but the universe's way of preserving this fundamental harmony for all observers. Our entire understanding of the cosmos, from the quantum field theories that describe particles to the grand curvature of general relativity, is built upon this foundational symmetry. That is why physicists test it with such exquisite care. They search for the tiniest crack in this perfect facade. If an experiment were to find even a minuscule violation of Lorentz Invariance or the CPT theorem, it would be like discovering that a perfect circle actually has a tiny flat spot. It would mean our most fundamental theories are incomplete. Such a discovery would be a direct portal to a deeper layer of reality, pointing toward new physics beyond the standard model, perhaps even challenging our very conception of the nature of space and time itself. The relentless, unbroken perfection of this symmetry is what holds our reality together, and the search for its breaking is the search for the next great revolution. These vast cosmic deserts are far from empty. Within their sprawling darkness, a hidden architecture repeats itself. A great void will often contain smaller, subordinate voids, and those will contain even smaller ones, all connected by faint, tenuous filaments of galaxies in a pattern that seems to recur at different scales. This is a fractal-like symmetry, a self-similar pattern etched into the nothingness itself. It is the cosmic web in negative, a grand, hierarchical nesting of absence. The immense Boötes void, a region of space so large it could contain thousands of galaxies yet holds only a handful, is not a solitary anomaly. It is the king of a dynasty of emptiness, surrounded by smaller voids that echo its structure. This is exactly what our models of the universe predict. The same Gaussian, scale-invariant seeds imprinted by inflation, once stretched and carved by gravity's relentless pull, naturally create this statistical recursion. The voids are not random holes punched in the cosmos. They are the inevitable, sculpted hollows that form as matter drains away into the filaments and nodes of the web. That we see this same pattern of emptiness repeating from the largest scales down to the smallest voids we can measure is a powerful and independent confirmation of our entire cosmological story. The symmetric whisper of the Big Bang gave us not only the great walls of galaxies but also this majestic, tiered cathedral of nothing, a silent echo of creation's first perfect order. The timeless symmetry of the Wheeler-DeWitt equation presents perhaps the most radical challenge to our everyday experience. This foundational equation for quantum gravity describes the entire cosmos as a single, static quantum object, a frozen moment of reality. Yet within its elegant mathematics, something essential is missing. The variable for time simply does not appear. At this most fundamental level, the laws governing the quantum fabric of space-time are perfectly symmetric under time translations, meaning they do not change if you shift the cosmic clock. There is no past, present, or future in this picture, only a single, eternal now. This is the profound problem of time. How does the relentless, flowing river of time we all feel emerge from a universe that is, at its heart, timeless? The answer may lie not in the whole, but in the intricate relationships between its parts. Think of a single, unmoving photograph of a bustling city. The image itself is static, frozen, but within it you can deduce movement and sequence. A car is blurred, suggesting speed. A person is captured mid-stride, implying a step before and a step after. Time is not in the photograph's paper, but in the relationships between the objects within the frame. In a similar way, our perception of time's flow may be an emergent property, a story told by the complex quantum entanglement of different subsystems within the universe. As particles and fields interact, becoming entangled, they create a web of correlations that defines a kind of internal clock. One part of the universe can act as a reference for the passage of time for another. This process effectively breaks the perfect, frozen symmetry of the whole. The flow of time becomes real for us because we are complex, entangled observers within the system, not outside of it. Your conscious experience of a moment, and then the next, may be the universe's way of reading its own internal correlations. A majestic symmetry broken into the beautiful, sequential story of existence. This 1 in a billion surplus of matter is the ultimate broken symmetry. The very substance of our being is a testament to a fundamental cosmic imbalance physicists call the Barrian asymmetry. For this overwhelming preference for matter to have occurred, 3 very specific conditions had to be met in the furnace of the early universe, principles first outlined by the visionary physicist Andrei Sakharov. Each of these 3 conditions is at its heart a requirement for a different kind of symmetry to be broken. The first condition is Barrian number violation. In our everyday world, the total number of heavy particles like protons and neutrons seems to be conserved, a stable symmetry. But for matter to be created from a state of perfect balance, this rule had to be breakable. There had to be a process, a new kind of interaction that could generate more baryons, the family of matter particles, than antibaryons. The second condition was C and CP violation, that cosmic lopsidedness we already see in particle decays. The universe needed a built-in preference, a rule that treated matter slightly differently from antimatter to tip the scales. The third condition was a departure from thermal equilibrium. The universe had to be out of balance, cooling rapidly enough that the processes creating matter could not simply reverse themselves. A perfectly symmetrical, evenly heated universe would have just oscillated back to perfect balance, erasing any budding asymmetry. Our existence, therefore, is not a gentle product of cosmic equilibrium. It is the direct result of these 3 violent symmetry breakings acting in concert during the universe's first fleeting moments. The great quest now is to pinpoint the exact mechanism. Did this happen at tremendously high energies in grand unified theories, where the forces of nature were one? Or did it occur during the electroweak phase transition, when the electromagnetic and weak forces split apart? Or perhaps through a process called leptogenesis, an initial asymmetry among ghostly neutrinos was converted into the Barrian asymmetry we see today. Unraveling this mystery is not just an academic exercise, it is the search for our own origin story, an explanation for the very stuff from which every star, every planet, and every one of us is made. 2 particles born from the same quantum event can share a single existence. Even after they are separated by the width of a galaxy, their fates remain perfectly intertwined. This is quantum entanglement, a phenomenon so strange that Einstein called it spooky action at a distance. It is not a force that pushes or pulls. It is a symmetry of information, a perfect correlation that is maintained instantaneously across any distance. Think of two coins, each spinning on its own continent. In our everyday world, flipping one coin has no effect on the other. But if these were quantum entangled coins, the moment you see one land on heads, you know with absolute certainty that the other has landed on tails, no matter how far apart they are. The correlation is perfect, a symmetrical link that defies our classical intuition about how the universe should work. This non-local connection challenges our deepest notions of locality, the idea that objects are only influenced by their immediate surroundings, and causality, the rule that cause must precede effect. How can information about a measurement seem to travel faster than light? The answer is that no information is actually traveling. The two particles were never truly separate entities to begin with. They are part of a single, unified quantum system. The universe, at its most fundamental level, appears to maintain a hidden symmetry of wholeness. The apparent separateness of things, the vast empty spaces between stars and galaxies, might be a kind of illusion. Underneath it all, reality is woven into a seamless web of instantaneous connection. This entangled symmetry is not a minor curiosity. It is a fundamental feature of quantum mechanics, and it hints that the true fabric of the cosmos is a deep, interconnected whole where every part somehow knows the state of every other part. Deep within the heart of every atom, the nucleus holds a secret alliance. Protons and neutrons, though one is electrically charged and the other neutral, are treated almost as identical twins by the powerful grip of the strong nuclear force. This near-perfect sameness is described by a concept called Isospin Symmetry. In this view, the proton and neutron are not separate particles at all, but simply two different states of a single entity, the nucleon. Think of it like a coin. A coin has two distinct states, heads and tails, but it is fundamentally the same object. The strong force sees the nuclear coin, not which side is facing up. This symmetry is so effective because the strong force is conveyed by gluons, which are utterly blind to the type or flavor of quark they are binding. It cannot tell the difference between an up quark and a down quark. Since a proton is two ups and one down quark, and a neutron is two downs and one up, this quark blindness makes the two nucleons nearly interchangeable under the strong forces domain. This is why the forces binding proton to proton, neutron to neutron, and proton to neutron are all almost exactly the same strength, creating a powerful, symmetrical glue that holds nuclei together against the tremendous repulsive force of the protons crammed inside. Yet this perfect mirror is slightly smudged. The symmetry is broken in two ways. First, the electromagnetic force, which only affects the positively charged protons, pushes them apart, creating a slight imbalance. Second, and more fundamentally, the up and down quarks themselves are not perfect twins. The down quark is very slightly heavier than the up quark. This tiny mass difference, a mere fraction of the mass of a proton, is enough to make the neutron slightly heavier than the proton. In the high-energy chaos of the early universe, when temperatures were immense, this small mass difference was irrelevant. The symmetry was almost perfect. But as the cosmos cooled and condensed, these subtle imbalances were frozen into the structure of reality, leaving isospin as an approximate, yet incredibly powerful, echo of a more unified and symmetric past. This broken symmetry is not a flaw. It is a fossil, a reminder of a hotter, simpler time, and it provides physicists with a master key for classifying the complex energy states of nuclei and predicting the outcomes of nuclear reactions that power stars and forge the elements of life. But what if this entire cosmic story, from the fiery Big Bang to the cold, dark end, is not a one-time event? What if our universe is just one note in an endless cosmic symphony, repeating in cycles of birth, death, and rebirth? This is the breathtaking vision of conformal cyclic cosmology, a hypothesis proposed by the Nobel laureate Roger Penrose. It suggests that the universe is not headed for a final, eternal silence. Instead, it is destined for a kind of perfect, symmetrical oblivion that becomes the seed for a new beginning. In the unimaginably distant future, all matter will have decayed or been swallowed by black holes, which themselves will have evaporated through Hawking radiation. All that will remain is a sea of massless particles, photons and gravitons, spreading out in an ever-expanding, featureless void. In this final state, the universe loses all concept of scale. There is no ruler, no clock, no way to distinguish something large from something small. It achieves a perfect conformal symmetry, a state identical to the highly symmetric vacuum from which our own Big Bang is thought to have emerged. Penrose's radical insight was that these two states, the infinitely large end and the infinitely small beginning, are mathematically the same. They can be seamlessly connected. The conformally symmetric death of one universe becomes the conformally symmetric birth of the next. In this model, the end of time in our eon is simply the beginning of time in the next. Our entire cosmic history, with all its broken symmetries, its galaxies, stars, and life, is just one episode in an infinite series. The mysterious, low-entropy state that gave our universe its arrow of time is no longer a singular, inexplicable miracle. It is an inheritance, a gift from the death of a previous eon. Penrose even suggests that the concentric rings some claim to see in the cosmic microwave background could be the imprints of colossal black hole collisions from the eon that came before ours, gravitational thunder echoing across the birth of a new cosmos. This is the ultimate symmetry, an eternal return on a scale so vast it redefines existence itself, where death is not an end, but a return to perfect balance and the promise of a new beginning. Our universe's unique set of rules may be a local ordinance, not a universal law. Imagine an infinite, eternal cosmic foam, where each bubble is a separate universe, inflating into existence with its own random selection of physical constants. This is the multiverse hypothesis, a landscape of realities where the force of gravity might be 1,000 times stronger in one bubble and completely absent in the next. In this vast tapestry, every conceivable symmetry and its breaking is realized somewhere. One universe might possess perfect supersymmetry, with every particle having its twin, while another might have a stable, symmetrical Higgs field, leaving all particles massless and forever racing at light speed. The specific gauge symmetries that gave us electromagnetism and the nuclear forces in our world, the precise mass of the electron, the very strength of gravity itself, all these fundamental fixtures of our reality become environmental accidents. They are not the only possible outcome, but simply the one that happened to occur in our particular cosmic bubble. This radically reframes the deepest question of all. It is no longer why do these specific symmetries exist, but why do we find ourselves living in a universe that broke its symmetries in this very specific, seemingly fine-tuned way? The matter-antimatter asymmetry that left us a world of substance, the specific strength of the strong force that allows for stable atomic nuclei, the exact value of the cosmological constant that permits galaxies to form, all appear to be exquisitely balanced for the emergence of complex life. In the multiverse, this fine-tuning finds a potential explanation. We do not observe all possible universes, only the rare subset where the broken symmetries accidentally conspired to create stars, planets, and observers. Our existence becomes the selection effect, a single, conscious data point in an infinite ocean of silent, sterile cosmos. The profound symmetries we have spent this journey unraveling are then both fundamental and incidental, the unique local dialect of a reality that speaks in every possible tongue. Symmetry is the fundamental language of physical law, a principle whose breaking has shaped every aspect of our reality. Our journey reveals that these patterns are far more than a pleasing aesthetic. They are the hidden architects of the universe, the CP violation that allowed a shred of matter to survive annihilation, the Higgs mechanism that gave particles their substance, the isotopic cosmos that grants us a coherent history to study, all stem from these strange and powerful balances. We are only just beginning to understand their full depth. As we build more powerful particle colliders and peer deeper into the cosmic microwave background with new telescopes, we are not just collecting data. We are learning to read the symmetrical code from which reality is built. The quest to decode these principles is the quest to understand existence itself. What symmetry or its breaking do you find the most profound? Share your thoughts in the comments and subscribe to continue exploring the deepest mysteries of the cosmos with us.